All right, here we are graphing rational functions again, and we're now ready for the B example. The degree of the numerator is the same as the degree of the denominator in this example. That's a little different than what we saw and what we'll see in these other examples. First step is to factor the numerator and the denominator. I'm going to do that. I saw that there wasn't anything in common that I could pull out on either of these. So I'm going right to the parentheses. 2x, 4x is how I would get 8x squared. And then I'll try 3 and 5. 3 times 4 is 12. No, that doesn't work because 12 and 10 is not getting me 26. So I'm going to flip those around. 5 and 3. Let's see, 20x and 6x. Yeah, 20x and 6x will get you 26x. That's a plus, so if they're both minus, it's a minus in the middle. Minus 20x minus 26, that works. Just use a little trial and error. I know there's that X method that organizes your thoughts, but it still comes down to trial and error. 2x and x here, 3 and 5, but it's probably 5 and 3. And the reason I say that is probably a minus here, because I have a feeling we've contrived this problem such that this will cancel, and that'd be nice. Let's hope that's the way it is. Minus 5x and a plus 6x does give me a positive 1x. So we're looking good here. In the second step, we'll reduce that, but I want to leave it like this for a minute because the next thing we're also supposed to do in the first step is determine the domain. In other words, we don't want 2x minus 5 to equal 0. Why not? Then the denominator would be 0, it'd be undefined. By the same idea, we don't want x plus 3 equal to 0. So 2x is not equal to 5, meaning x cannot be equal to 5 over 2, and x cannot be equal to, what is that, minus 3. So the whole business here for the domain, the set of all x, that's the way I read this. I look at this set, the curly bracket, that says the set of all x such that, the two dots I think of as such that, x is not equal to what? 5 over 2, and it's not equal to minus 3. So when we go to graphing this, we already see our vertical and horizontal asymptotes. We've already identified them. Do you see why? Do you remember from the previous one why that is? The previous example? Already in step 1, I'm only in step 1, and I see that I have vertical asymptotes at minus 3, x equals minus 3. We don't want x equal we don't want x to be equal to minus 3, and so this little, think of these asymptotes as kind of a little force field that says nope, the function's never going to cross where x is equal to minus 3, and x is equal to minus 3 everywhere along that vertical line. And then 5 over 2, well, that's 2.5. Okay, so at 2.5 we have a vertical asymptote. Yeah, that's about 2.5 right there. Up from there, try and keep it parallel to the y-axis. Should label that. That's the y. Actually, it's not really the y-axis. It's the g of x axis, right? G of x. Okay, that's the way we have it. And here's x. Those are our asymptotes. So we have g of x equals 2x minus 5, 4x minus 3 over 2x minus 5, x plus 3. All right, so we have the factorization came out to this in the previous example, or the previous step. We have this that I'm moving on to in step 2. And I'm going to cancel what can be canceled. That's what step 2 is. It says reduce to lowest terms. And so 4x minus 3 over x plus 3 is the lowest terms. Step 3 is to plot the intercepts. So now that we've reduced to lowest terms, we see y equals 4 as the horizontal asymptote. You've got it reduced. It's the leading coefficients or in each polynomial. They're of the, if it's of the same degree, and it is, x to the first, this leading coefficient, 4 over 1. So 4 over 1 is just 4. So my horizontal asymptote is right up here. Right through the 4 there. Okay. I'm gonna see if I can copy that and bring it down. So I want to bring that graph down where we can see it here. Okay, y equals the 4 is the horizontal asymptote. We got that out of step 2. Step 3 is to plot the intercepts. I'm going to write this one out. Maybe I should have been writing it before. Find the intercepts. Now that it says g of x equals 4x minus 3 over x plus 3, we're set to find the x-intercepts. Well, there's only going to be one. You find the x-intercepts by setting g of x equal to 0, and that's only going to be 0 when the numerator equals 0. You don't want the denominator equal to 0. You know what? We remember that. Okay, so 4x equals 3. We divide by 4. We see that we have x equals 3 over 4. That's going to be an x-intercept. I'm going to plot it. I'll plot it in blue here. That's supposed to be 3/4 of the way to 1. Maybe I can expand that. It's too... See what happens if I try that. Okay, that's a little better. I hope it's still on the... So x equals 3 over 4. That's an x-intercept. That's interesting. All right, let's find the y-intercepts. I'm going to shrink this down. This took up too much room. Let's find the y-intercept, and you do that by setting x equal to 0. So now we'd say g of 0 equals 4 times 0 minus 3 over 0 plus 3. And that gives us a minus 3 over 3, which is minus 1. The y-intercept is at minus 1. All right, now here's a good question. It's true that the horizontal asymptote can get crossed in this middle section here. It won't be crossed out here. In other words, either the function will be doing this and maybe this, or some variation. In other words, a variation such as the function may come down like this. We don't know that part yet. We'll find that out. But in here, we've seen them do this kind of thing where they go down and then they come back up. But why is that not going? That turns out that's not right. And why is that not right? Why is the function not coming back up? Why do you think it's not coming back up? We found an x-intercept at 3/4. If the function was going to come back up, we would have found an intercept back here as well. And we didn't. So the function can't go back through there. And so I'm going to erase that curve. I know for a fact that the function's curve is going to come up like this. It wants to get close to that asymptote, and it's going to S its way through here. It's kind of an S. And it's going to come on up here, and it wants to get close to this asymptote. Now it's crossing the horizontal, but that can happen. It can cross the horizontal, but it won't at some point in the middle here, but it won't cross it out at the extremities. It's not crossing the vertical asymptotes anywhere, and These functions will never do that. Okay, so that was step 3. Step 4, I'm going to shrink that one too. Step 4. So step 4 is find the horizontal asymptote, and step 5 is find, or actually it's the other way around. Step 4 was to find the vertical asymptote. Step 5 was to find the horizontal. But as you notice, we've done these, we already found them. They're the dotted lines that we see here. In other words, the vertical asymptotes, I'll abbreviate it, vertical asymptotes here at, what are they? X equals, that's an equation of a line, x equals -3, and x equals 5/2. We also have the horizontal asymptotes at, where do we have them? Oh, it's only, of course there's only one, and it's at y equals 4, or also known as g of x equals 4. So that's how that's working. All right. Well, it looks like we've already got part of the graph drawn, as you'll notice here. Now we need to determine whether the graph goes this way, or, taking that off, if it curves down here. And so we'll work on that left side to determine that. It's going to do one or the other. And so the way I find that out, let me shrink all this business up over here, get it out of the way. Okay, I'm going to use this room in here. Okay, so I'm just going to use a little table, and I'm going to say, okay, here's x and here's g of x, and the function g of x, I see a little version of it here. X at x equals, okay, so for x equals -4, are we up in this area? Are we going to do one of these, or are we going to do one of these? And that is determined by plugging it in. In other words, g of -4 is equal to what? Well, we'll find out. If we plug in a -4, so to determine g of -4, we can use the reduced version. The other stuff that was in there would just cancel. So g of -4 is equal to 4 times -4 times -3 over -4 plus 3. That's what I'm looking at, that little version of it up there. I messed up. Okay, so that's what we're getting here. And I want to know, is it a number that's greater than 4 or less than 4? You see why I'm asking that? Right here, I want to know whether it's up, when I look at the graph there, is it above the horizontal asymptote or below? Well, let's see, we got a -16 minus 3, that's -19, over -4 plus 3, that's -1. It's a positive number, which I would hope to see. Okay, and 19 over 1 is just 19. So it says what this is telling me is that g of -4 is all the way up at 19. So at -4, I know that my graph is way up. My graph is way up off of where I have it, but I can tell that it's going to be doing something like this. It's going to go way up there. So let's get that in there in the right color here. So it's going to go way up there like so. And so at -4, we're way up there. And let's see what happens at +4. G of +4. Why am I trying to find that out? I'm doing that because I want to know whether the graph does this or this. I don't know which one of those it does. It's not going to do both, by the way. Wouldn't be a function, for one thing. Okay, so let's try g of +4, see what happens. I'm plugging it into this version. And we're seeing 16 minus 3 over 7. what is that? 13 over 7. Let's write that as a mixed number. It'll behoove us to do that here. It'll be easier to see. That's 1 6/7. It's almost 2, but not quite. 1 6/7. So that's telling me that at 4, we're only at 1 6/7. We're right here. And so I can draw my curve this way for this part. So this is what the graph looks like. It's if I take it like this and shrink it a little bit, and I can bring it down here, bring it where we can see it. This is what our graph looks like.